there's one thing I've learned about astronomy: when something works, never touch it again. No worry, you're good, you're good. Okay, so that being said, I'm gonna need to give you all a little bit of background on this, because there's a lot that I will need to get through. I figured, so I figured I'd be a little transparent about this. There will be lots of pretty pictures. It's not gonna be mostly text, I swear. So while I say this talk is about jellyfish galaxies, I'm going to need to do some pretty serious tangents, math nerds? About into galaxy clusters, how galaxies interact and the physical processes involved in that, and some aspects of overall galaxy evolution, or how galaxies form and develop with time. I'll show you lots of lovely images of these galaxies. And it also gave me the idea that I wanted to talk about one more type of a weird morphological galaxy, ring galaxies or wheels. And I wanted to let you know that, and I also wanted to let you know what we don't understand about these galaxies and the processes around them, because I think that that's particularly interesting, just because I'm a scientist. But I also wanted to give you all some ideas of how you could actually help us to answer these questions. So let's see, and we'll end with some key things that I'd like you to remember for the talk. I did draw you in with the promise of an interpretive dance, but it's been a while since I've done this dance. But I have some other things in mind. I did dress quite purposefully, just to give you all a little hint. So it will give you a little taste with a little bit less of the difficult dancing that I did for the original performance. And I hope you all enjoy. So, astronomers that study galaxies are a little bit of a weird bunch. Sometimes we don't quite understand our motivations for what we do. And honestly, it's just because I think they're neat. That's it. I think that they come in a beautiful variety of morphologies, and how they get there is very diverse. There is no real one path of a lifetime or one path of evolution for galaxies. There are internal processes that can shape a galaxy and its properties. Things like outflows and feedback. So gas being forced out by, say, supernova winds or black holes, and the accretion of gas into a galaxy when it's still rather young will affect the properties of the galaxy, how stars form inside of the galaxy. There are external processes such as mergers that will affect the processes of the galaxies as well. But there are sort of three main types of galaxy. There's ellipticals, which are big and red and spheroidal. They tend to be a little bit more chaotically dominated when it comes to their internal motions. So rather than there being a coherent rotation or something like that, it's a little bit more like, if anybody has studied like thermodynamics, the random motions of, say, gas particles. They tend to be red because stellar populations are a little bit older and they're a little bit more gas poor. Contrast that with a spiral or disk galaxy, which is like the galaxy that we live in. These galaxies tend to be bluer, if you can see, lots of nice blue areas around here. That means that the stars that are being formed are massive and younger. Big young stars that don't live as long tend to be blue. And there's lots of beautiful dust lanes, and they tend to have sort of a core that has a older stellar population. They're also very gas rich, and there's ongoing gas formation in most of star formation in most of them. And then there's the irregulars. The irregulars are sort of like a other category, but I think that's where the most interesting stuff is happening, just because they're very weird looking, and they can come in pretty much whatever shape you can imagine. Like when I give this talk to kids, when I talk to kids about galaxies, I like to point out like this particular galaxy because it kind of looks like a vomiting hummingbird. Can anybody else see that? Yeah, so like here's the vomit, here's like the wing and the beak. But that's just one example. There's also, this is one of my favorite galaxies that I see. It looks a little bit like a rose. There's mice friends. Sombreros aren't actually that weird. This is just a basic disk galaxy, but it still legitimately looks like a sombrero, right? And then this is supposed to be antennae. To me, it just looks like a mess or a hot mess. But let's see, what else did I want to say about these things? Usually what creates these really wacky morphologies are these external processes that I referred to earlier, things like mergers, things like we call it galaxy harassment, where there's a ton of other galaxies around one galaxy, and all the gravitational pulls will cause weird morphological effects to happen. Or tidal tails can form because, like for example, this is sort of a forming tidal tail. Stars and gas are being ripped off of this particular galaxy. That creates these big long tails. You can get pretty much any shape you want in a galaxy. I would recommend, so I found this actually, one of the other astronomers at U of T sent this to me because I sent out a big thing. Send me the weirdest galaxy you have ever seen. And they, one person recommended this website to me. So you can use that little handy tool to pretty much spell out whatever you want. Because again, galaxies come in such a wide variety of shapes. What they're doing is they're just matching the letters to whatever galaxy kind of looks like it. I got major brownie points with the boyfriend the other day because when I was playing around with this, I sent him something, I love you, Jacob. And he's like, oh. Like, that took me 5 seconds. Brownie points for me. But as I talked about, my favorite galaxies are the jellyfish galaxies. And this galaxy right here, ESO 137001, we're lovely with naming, aren't we? Is sort of a nice prime example of a jellyfish galaxy. Why do we call it a jellyfish galaxy? Because it looks like a jellyfish. So it has these long gaseous tendrils. These are created by tidal forces, as well as ram pressure stripping. There is sort of like a jellyfish body head area where most of the stars and dark matter is. You can also see a little bit of trailing nice blue stars here. Again, whenever you see a big blue star clump, that's usually ongoing rapid star formation. What else do I want to show you? So yeah, you see the nice trailing young stars there. And one kind of important thing about this is that the ridiculous majority of these galaxies that we see come from really dense cluster environments. So the stuff that I study. What I mean by a dense cluster environment is if there's a lot of other galaxies around that galaxy in particular. So let's talk a little bit about galaxy clusters then, because they're kind of an important part of this jellyfish galaxy morphology. And I like to kind of refer to it as a dance party because galaxy clusters, everything's moving around super rapidly. You may not even understand what's going on. It reminds me of being a little bit at like, does anybody go to like heavy metal shows in the mosh pit? It reminds me a little bit of a mosh pit. So what really is a galaxy cluster? So this is sort of an example of a galaxy cluster. I'm going to get my notes because I have a way I like to go through this so I don't forget everything that I want to tell you all. All right, so what is a galaxy cluster? It is a group of gravitationally bound galaxies inside of a big, massive dark matter halo. So how do we know it's a dark matter, that there's dark matter in there? Because the galaxies are moving a lot faster than we would expect them to be if there wasn't extra mass there. But we can't actually see it, which is very annoying for me. It's held together by that huge halo, and that actually makes up the vast majority of the mass of the galaxy cluster. Very little of the mass of a galaxy cluster is actually in the galaxies themselves or their stars. So let's see. As an example, we have sort of our local supercluster group here. And so we're not really in one of the main nodes of this group. We're sort of in the boonies there, in the local galactic group, us and Andromeda and all of our satellites. And then there's this big old Virgo cluster, which I have a nice picture of here on the right. So this is an HST image of that Virgo supercluster. So that's our closest galaxy cluster to us. We are not inside of it yet. We're in what's called a galaxy group. It's not really a cluster. A group is somewhere between 2 to 6 galaxies that are gravitationally bound to each other. It's only really us and Andromeda that are within that galaxy group, and she's coming right for us. But one important part of a galaxy cluster is what's called the brightest cluster galaxy, or the BCG, or brightest central galaxy, whatever you want. It's sort of something that we've gotten into minor fisticuffs with other astronomers. So this is the brightest cluster galaxy, Messier 87. Notice what kind of galaxy does this look like to everybody? Yeah, it's elliptical. Perfect. So these brightest cluster galaxies are some of the biggest galaxies in the universe, and they tend to be elliptical because, again, mergers kind of shape the process of these galaxies. Since they're kind of in the middle of that big dark matter halo, everything comes right forward, and it really messes up the original morphology of the galaxy and leaves it sort of this big puffy elliptical. And there isn't a lot of ongoing star formation inside of them. And other notes. Also, notice that most of these galaxies that you see are quite red. That's kind of an important detail. And you don't see a lot of spirals. They look mostly elliptical or irregular. Also important. So here's a nice little schematic of a galaxy cluster that I wanted to show you all. You don't need to read anything on the top. I'll explain everything to you. This was just the best image I found. So we have our nice BCG in the center of a galaxy cluster. Sometimes it's not right on the center, but it's close. Oftentimes these big central galaxies have lovely jets coming out of them. That was also the other possible talk I could have given, but I wrote a paper on this recently. And sometimes when you write a paper on something, you don't want to look at it again. But it is still quite lovely. What happens is there's a lot of, this red area around here is actually what makes up most of the matter content of a galaxy cluster. It's called the intra-cluster medium. And that's super hot gas. It's so hot that it actually glows in X-ray light. So when people are looking for galaxy clusters, one of the things they can do is actually look for spots of X-ray light. Because again, the gas is so hot, glows. One of the fun things that I saw in one of these big clusters is that the BCG had these active jets. These jets are from a very, very, very big supermassive black hole that is actively consuming gas or stars. And when it does that, you see these beautiful jets come out and they create little holes in that intracluster medium. And you can actually see cavities where there isn't any of that intercluster medium light coming from it. So you'll see sort of this double lobe structure, and it can actually create ripples, which are like sound waves inside of that galaxy cluster. And so galaxy clusters are sort of the biggest thing in the universe that you can call a thing. So because this is a gravitationally bound structure. Let's see, what else did I want to, and then there's a bunch of galaxies falling into it at all times, and sort of toward, there was a paper when that came out in the early 2000s that talked about something called the morphology density relation, or the color density relation. So as galaxies get closer to the center of a galaxy cluster, they appear to be redder, and they appear to be more spheroidal and elliptical. You get more of these blue disk-like galaxies as you get toward the edge of a galaxy cluster. So there's a bit of a gradient there. So I showed you a schematic. Let's show you some real data now, because I love actually looking at real data. So these are sort of the components of a galaxy cluster that you can look at. So there's dark matter, which makes up most of the mass. And again, you can't see it, but you can sort of guess where it is by doing something called gravitational lensing, or weak gravitational lensing, where you're measuring the distortions that space-time makes on the light of galaxies behind the galaxy cluster. Einstein was a genius for figuring this out. There's also the hot gas. So that glows in the X-ray. That is that intercluster light I was telling you all about, or the intercluster medium I was telling you all about. Super hot because everything is falling in toward that the center of that gravitational potential. And since all the gas wants to get into that center of gravitational potential, anybody who works on cars will tell you when you compress gas, it gets super duper hot, which is what you're seeing. There's also these stars, which are optical light. You can see all of that here. There's also some lovely little tendrils coming out through here. That's also something I found in the BCGs of the galaxy clusters. These are these tendrils come from the jets, actually, from very early parts of the black hole jets. And speaking of black hole jets, you can actually measure those using radio. You can see that sort of elongated structure that will eventually be sort of blowing bubbles in that hot gas. There's warm gas, which you can also measure with optical light as well, and cold gas using microwave astronomy as well. But I haven't gone into that, and I don't think it's quite as entertaining as galaxy clusters and super hot gas. So, an important thing about we touched on this a little bit, but galaxies in denser environments are redder. They have lower star formation, they have less gas inside of them. So less gas actually bound to them, even though they're sort of constantly swimming or moshing through this sea of super hot gas, but it's not bound to them. So it's not forming stars. So this is a nice little picture. Please ignore the jargon. But basically what this means is the density of the local environment. So the more galaxies that are close to a particular galaxy, that goes this way, versus the color of the galaxy, so how red that galaxy is. And generally you'll see that bigger galaxies and galaxies that are closer to, that are in denser environments will appear redder, larger, fluffier, either more irregular or more spheroidal. You don't tend to get a lot of really nice disks like you see with the Milky Way and Andromeda. But for a while, we didn't really know why that was the case. And there were a number of processes proposed for this, but this is actually where we need to start talking about some other things like galaxy structure. So galaxy structure. So now we talked about the structure of galaxy clusters. Let's talk about the structure of the galaxies themselves. So galaxies themselves also have a dark matter halo because, and we can't see those, but we can actually measure the amount of dark matter in a galaxy by looking at the internal kinematics of a galaxy. So how fast things are rotating inside of the galaxy or inside of the galaxy's halo. And let's see, this is a disk galaxy in particular. So not all galaxies look like this, but say it's a disk galaxy. There's the disk area, so that's like where we are in our Milky Way. That's where most of the ongoing star formation tends to be in an actively star-forming galaxy with lots of gas inside of it. And then there's the galactic bulge. That's sort of a older part of a disk galaxy that forms earlier in its life. Disk-like galaxies we're finding tend to form inside out. So dark matter, the bulge, the disk, there's more to it as well. Here's our friend Andromeda here. So Andromeda has old stars, which are a little bit redder, more yellow, more towards the center. You see baby stars in the outer regions of the disk, and there's a lot of dust there because these super high mass young stars are actually what forms dust, and therefore us, we are stardust. And my favorite part of the galaxy, because actually it's the easiest to measure observationally, is the warm star forming gas. I love warm star forming gas because it glows a beautiful red. So what this warm star forming gas is a bunch of hydrogen pretty much that cloaks these young stars, these young blue stars. They're like birth clouds. You're all amateur astronomers. You've seen the Orion Nebula. It's that. But it appears red because if you light up, say, a hydrogen lamp, if you have a hydrogen lamp around sometime, you can take a look at the light that is released from it via quantum mechanics. There are very specific emission lines. And my favorite emission line ever that I based all of my work on, even now, is called hydrogen alpha, and it glows beautiful red. So that's why this is red. So galaxies have gas, they have stars, they have dark matter. Most of the mass is in dark matter. The rest of it, most of the rest of it is in gas. Only a little itty bit of it is in stars. All right, so we need to talk a little bit about collisions now. So when galaxies interact with another galaxy or with a galaxy cluster, that's where you get your weird morphologies. So let's talk first a little bit about galaxy collisions. So here is a lovely video I found ages ago. I think it was by NASA of showing a simulated galaxy collision. So this is what we call a major merger. These galaxies are about the same size. Most galaxy interactions are not same size. Most of them are, one galaxy is quite a bit bigger than the other. Oh, and then we see actual images taken from Hubble that match up with this, with these, with the angle and with the part of the interaction that they are in. So what you'll get is you'll get warps in the actual disk structure. You'll see some of the gas and stars is peeling off. These are tidal forces. Very pretty. And as I talked about before, it looks like a little bit of a train wreck, but those are my favorite kinds of galaxies. So you can see them come apart. It's like a beautiful dance. This is why I love galaxy interactions. Galaxies are like a box of chocolate. You never know exactly what you're gonna get when you get a galaxy merger. So these are some of my favorites. And I'm just waiting for the last bits of it. Because we have more to go on to, but it's a very pretty one. That's pretty cool. Yeah, it is. I love Hubble. Okay. That's why I got it tattooed on me. Oh. Also, happy birthday to Hubble recently. Yeah. It turned 34. I remember because it was launched the same year I was born. We were both launched into the world the same year.
Did you need corrective optics?
Surprisingly, no.
Ah, there you go.
Astronauts have to visit you
to get me all fixed up? Yes. I do not like going to the doctor.
Yeah.
But you gotta. And yeah, so you can get a huge variety of galaxy morphologies depending upon the stage of a merger that a galaxy is in and the angle at which you are observing it. All right, so why was that so important? Because so when you slam two galaxies together, this is our little train wreck galaxy that we were looking at earlier. So this is actually two galaxies. You can see two different sort of bulge cores. So this looks like it was previously two disk-like galaxies, and they rammed into each other, and you see the dust sort of between them. You can't really tell which dust belongs to which one. But what I find particularly enjoyable about these galaxy interactions is that you get these huge bursts of star formation. You see an enormous amount of this blue light. So again, when the gas is compressed into a small amount of space, the gas will eventually ignite, and there will be something called a starburst, or a period of super rapid star formation when they slam together. So that's also an important thing for jellyfish galaxies. Also, another important thing is, so this is an example that's not really a galaxy-galaxy interaction. This is actually a collision of two galaxy clusters. And so we talked about the different parts of a galaxy and a galaxy cluster. There's the stars, there's the dark matter, and there's the gas. So the thing about those is that they all have different ways they behave during a collision. So dark matter can be measured using weak gravitational lensing, and generally this is a picture. This is a simulation of something called the bullet cluster. I also have that tattooed on me. The blue represents where the dark matter has been determined to be via weak lensing. You can see where all of these stars are. Those are the white and yellow areas, and the gas is in pink. That can be measured using X-rays. So this particular galaxy cluster, you'll see them interact and you'll see a little bit of a shock wave form. So I'm going to start this for you so you can actually see what I'm talking about. So here's a happy little galaxy cluster, just minding its own business. And somebody else has to plow through. And you see the shock wave of light form, the shock wave form. So that's why they call it a bullet cluster, because it kind of looks a little bit like a bullet. Anybody want to see that again, or should I move on to the actual picture? One more time?
What's the time span?
God, very, very, very long time. I'm not actually sure of the numbers, but it would be in I would say million to billion years range.
Yeah.
Yeah, it would take a while. All right, so here's the actual image. So let's see. We have our dark matter, we have our gas, and we have our stars. And yeah, cats. So what you'll notice is that the bullet cluster was a very important observation and discovery for astronomers, because it actually allows us to look at how these individual parts of a galaxy cluster or a galaxy will behave when interacting. So if you'll notice, the gas seems to be peeled apart from the dark matter. Generally, the gas and the dark matter occupy about the same space when an interaction isn't happening. But when interaction does happen, the gas is collisional, as we call it in astronomy. So the gas slams into itself and heats up. It doesn't pass through each other. It takes a little while to disengage if they're passing through each other. Whereas the dark matter and the stars seem to have passed right through each other. So they don't seem to be interacting at all, well, other than gravitationally. But that's in the case of dark matter, it's because we don't think it has any electromagnetic interactions with anything else, hence being dark matter. That's why we don't see any light coming out of it. Stars, people don't realize just how far apart everything is in the galaxy. You can slam two galaxies into each other, and the stars are probably not actually going to hit. I give the example of if I shrunk the sun down to about this big, held into my hand here in Toronto, I think the closest star, Proxima Centauri, would be located in Atlanta, Georgia. Yeah, so things are very far apart, so the stars just sort of pass right through each other, and the gas, it's not. Very important. All right, so now let's get back into jellyfish galaxies, what we came here to talk about. So our friends here, James Gunn and Richard Gott, in the 70s wrote a very interesting theoretical paper about something called ram pressure stripping. So this is sort of a nice little cartoon of ram pressure stripping. Sorry, I'm going to give you just a little bit, just this is a touch of that. This is the formula for ram pressure stripping. It talks about the behavior of how this force will act upon a galaxy. So we have our pressure, or ram pressure, E of R, is proportional to the density of the medium that it is going through and how fast it is going. So if a galaxy passes through something that is very dense at a very fast rate, there will be a pressure exerted on the gas inside of it. So this is a nice little picture of a galaxy trying to enter a galaxy cluster, but there is a wind of the intercluster medium that will slow it down. So when that happens, that pressure from the hot cluster gas collides with the galaxy's gas and it drags it off, forming these lovely little tendrils. This is a simulation, this is not real data. And the appearance that you'll see varies quite a lot based on how it is oriented relative to you and at what stage of the peeling is going on. So this is 40 kiloparsecs. Should I convert that to light years? It's about 4 light years per parsec. So that's about 80 kilo light years in size. So you start out with these very short little tendrils. Looks a little bit like a SpongeBob style jellyfish, little tiny ones, whereas when you get to a later stage of that process, you'll get something that looks like maybe like a little bit more of a man-o-war type of jellyfish with super long tendrils. Yes, let's move on to This is an artist's impression of how that would work. So this galaxy is traveling through a galaxy cluster, and as it hits the gas inside of that galaxy cluster, you start to see these little tendrils form. And they're sort of dragged out along the path of the galaxy as it falls into that gravitational potential. Real pretty. And in addition, in these tendrils, there will be star formation happening because of the pressure that is exerted. All right. So now we talked a little bit about jellyfish galaxies. Let's talk about like some individual jellyfish galaxies, and that way we can look at some pretty pictures and talk about exactly what's going on in them. All right, so this is one of our closer jellyfish galaxies, IC 3418. It's in the Virgo cluster. So this galaxy is falling into the Virgo cluster. Let's see. So you'll see the tail is sort of showing this nice peeling. Notice that it's quite a bit bluer than the main body of the galaxy, which appears sort of a white, reddish, yellow color. Let's see. So this is a composite image, as we were talking about. So that's when they put different wavelengths of light together so we can actually see what's going on with the galaxy. Let's see. So yeah, they did this using far ultraviolet light, so super ultraviolet light that is also released during star formation, and visible light as well. This is the one we've talked about a fair bit, ESO 137-001. Unforgettable name. That's your name. All right, so super duper long tendrils. Keep in mind though that most of this is actually X-ray. It's not the same X-ray as that is released from the galaxy cluster itself, because this gas is slightly cooler, but you can still see it in softer X-rays. It's located in the Norma cluster, which is near the Great Attractor, which is a big supercluster. It's moving super duper fast. Remember, we talked about pressure from ram pressure stripping is proportional to the density and speed. Speed is a big thing. Also, since you probably want to actually figure out how long these things are, this is 260,000 light years long, this table. So yeah, and again, you can see these little spots of star forming clumps. All right, this is sort of an early stage of ram pressure stripping because you don't have a big long state. You mostly see just these little clumps. So it's not quite as elongated. I don't remember which cluster this was part of, but it was more recently released. And again, you can see the main body is rather yellowish red, and you see the star formation sort of trailing behind the actual path of the galaxy's travel into the cluster itself. All right, and this is the last one we'll briefly go over, but this is JW 100. There was a fantastic group in Italy that over a few years was doing a very special study of ram pressure strip or jellyfish galaxies, and they actually created something I'm going to show you that's really fun. But they did 3D modeling of some of these objects used by looking at their kinematic data as well. And so again, we see this is sort of traveling face on into the cluster. So we can see that there's some pulling that way. There's a big difference in the color that you see as well. So now that I've gotten here, I want to show you this cool little tool that they shared with a bunch of astronomers. All right, so I'm going to see if I can full screen this. So they actually did a analysis. Let's see, I'm going to have to exit out of here so that I can move through here. All right. So we're going to jump to different views so you can actually sort of see how this is going. So this is the stellar light in white. I can take that out and put it back in. And so these layers that are colored have to do with different light that is emitted from elements. The one that I care the most about is hydrogen alpha. So that's the red. It extends the longest as well. So I'm just going to get rid of the O3 and N2 just for a little bit of a clearer image. And as you can see, what you're actually seeing depends very much on your angle. And I just wanted to play around with that because it's pretty fun to drag and move around. They also have a few other galaxies as well that I'm briefly going to look through. All right, so this is another ram pressure stripped galaxy. I'm going to get rid of O3 and N2 just for simplicity, and we can move around. So this is a very early ram pressure stripped galaxy, as you can see, because there isn't much of a long tail. And that's pretty nifty. And then our last one. Also, the fun thing about these is that if you have a VR headset, they're actually VR compatible. But I do not. I'm actually not a gamer. And yeah, this one's a really odd shape. It looks a little bit like a rocket taking off. Anyway, so just something to play around with if any of you are interested. All right, I'll get back to the slideshow. All right, so those are some individual galaxies. And since we're talking about weird galaxies, I also kind of want to talk about another kind of weird morphological galaxy. This type of galaxy is called a ring galaxy. This is sort of our most beautiful example. And this image is taken recently from JWST. JWST does some amazing stuff. So a wheel or a ring is the result of a face-on, perfectly right in the kisser collision with another galaxy that isn't as big as it. So what happens is you can see sort of the main galaxy structure here. So this is actually the main part of the galaxy. This is the disk previously. But after another galaxy goes through that galaxy, the gas is sort of compressed and then forms a shock wave that propagates outward, and that creates that ring shape. And if there were spiral arms in that galaxy, you can get what looks like spokes as it comes out. Additionally, star formation happens because, as you'll notice, lots of blue stars. So that's a nifty kind of galaxy, and that's real. But I also wanted to show y'all another simulation of how this would look in a simulation for what that actual collision would look like. So what this simulation is this top row. These are the stars. This is the gas on the bottom, and these are two different. This is a face-on and an edge-on view of what's going on, so that you can have sort of an idea of how this shock wave will form and propagate out. All right, so you can see the smaller galaxy moving toward the larger galaxy, coming right for it. Cosmic eons, huh? And we see a little bit of a disk distortion happening. All right, back so that I can. All right, you can see the gas starts really compressing quite a lot for the center, and it'll propagate outwards, forming that shock wave. And as you can see, there's this circle or ring shape that forms. However, the original morphology seems somewhat unchanged. You can see the galactic the shape of the galactic disk in there still, whereas you have a nice little ring of gas around it. So that's pretty nifty. So I'm just going to go back so you can see how similar that looks. So yeah, that's what astronomers think happened there. And just to toot my own horn a little bit, I also wanted to talk about this because a few years ago, some friends of mine and I actually got some imaging and some spectroscopy of what we think is the most distant ring galaxy that has been found. This would be about 11 billion years ago. So, because as you look further back in time, you're looking at earlier stuff. So it's about 11 billion light years away. And I just wanted to brag about this because I took the data on the Keck telescope. So this is the actual data. The problem is when you look really, really, really far away, things mostly look like fuzzy pixels. But we also have an artist's impression of what this actually looks like. So this is what they think it looks like. And they also created, again, another simulation for how this works. So we see a galaxy coming right for it, right in the kisser. Boom. And that shock wave extends out. But that galaxy isn't gone quite yet because gravity is gravity's a force. And so it starts falling back. Which is pretty nifty. And then when this is done, I'll move back so you can see how similar it looks to what we were actually visualizing. All right. So yeah, our data and the simulation. All right, so you don't need to pay super close attention to these, but I wanted to talk to y'all a little bit about the bigger picture of galaxy evolution and why this stuff matters. So just to show you how galaxies start forming, for a long time they were debating, astronomers were debating sort of what they call the bottom-up scenario of galaxy formation, where galaxies are a bunch of little things that come together to create one big thing, versus the top-down model, where galaxies form from a big cloud of gas that collapse into, say, a disk or a spheroidal shape. But of course, the reality and what the data is showing is kind of a mix of the two, right? That nature doesn't really seem to make things easy for us. Why this matters is that these dynamics tell us a lot about the formation in general of galaxy clusters and how galaxies themselves form. So and after formation, galaxies actually don't have what we call an unlimited life. So galaxies will eventually stop forming stars. A galaxy has to have a fresh supply of gas occasionally in order to have more gas to form stars. So astronomers are curious why galaxies stop forming stars, and there's two main pathways that have been studied so far. One is called mass quenching. So this can happen to any galaxy anywhere when it gets big enough. Once a galaxy gets big enough, there are processes such as supernova feedback. There are processes such as black hole feedback. So this is gas being forced out of the galaxy by these processes, because supernova are big explosions and can force gas out of the galaxy. Whereas black holes, we saw those jets, for example, that can also force gas out of galaxies. And so people are thinking once galaxies reach a certain mass, that just happens more, and the gas will leave the galaxy. And so the galaxy can't form more stars. There seems to be sort of an upper limit of how big galaxies can get without doing something like merging. Whereas those of us who are interested in galaxy clusters have noted another pathway for galaxy star formation quenching. And that is what we call environmental quenching, which is basically what I've been talking to you about for most of this talk. The galaxies interacting with each other, either pulling the gas out of the galaxy, or and that can be one big swoop, like with a ram pressure stripped galaxy. Or it can be smaller changes in the galaxy, such as what we call galaxy harassment, where there's a bunch of galaxies pulling on another galaxy tidally. Or something called starvation. We really have some terrible names for these. Galaxy starvation. Oh God, this is so sad. Galaxy starvation is when a galaxy, it may not be undergoing ram pressure stripping, but there isn't any new gas that falls onto it in a galaxy cluster, because a galaxy cluster's gas is just too hot to really fall on a single galaxy we're finding. So just no new gas forms, and it runs out of the gas it has. So those are sort of an overall view of how galaxies form and change with time. And jellyfish galaxies are actually a pretty big part of figuring out how that all works. So we're getting close to the end here, but we have some open questions about how all of this works because the problem that I found with science is that when you find the answer to one thing, it just leads you to 20 more questions. Very frustrating. So some things that we wanted to know about jellyfish galaxies and their implications for the rest of the universe is so what other processes might be happening in these galaxies, jellyfish galaxies? There could be, there was another process that we studied called overconsumption, where ram pressure stripping and a supermassive black hole having feedback in the center will actually, the supermassive black hole sort of push the gas out, and then the ram pressure stripping will pull it all out. So it's like super duper fast shut off of star formation. How does environment play a role? So how does galaxy morphology and star formation vary depending upon at what stage of the infall happen? That's actually what I've been studying for the last year, and it's very hard to tell. Starbursts are also a very important part of this. So what triggers the star formation in the central regions of a jellyfish galaxy? Because we still see a little bit of star formation in that central region. How long does it last after stripping against? Does the supermassive black hole do anything to trigger star formation? Because most galaxies have a supermassive black hole in their center. So what happens to these galaxies after they're completely stripped? Do they form into passive red galaxies? Do they still keep some of their gas and have another starburst at some point? Also, jellyfish all look a little bit different. Are there different subclasses based on what kind of cluster it falls in? Because maybe a younger galaxy cluster that doesn't have quite as hot of a intercluster medium might have different properties in its jellyfish galaxies. So what dominates? And what do the very beginning stages of this process look like? Because one of the problems of studying jellyfish galaxies is that jellyfish galaxies, you pick them out because they're rather visually impressive, right? They have these big long tails, but that's not how they start out. We don't really see the beginnings of this. Also something I tried to study, because it turns out measuring the offset between the gas and the stars can be a little bit difficult in these super early stages. And also I'm looking at galaxies that still have gas in them inside of a galaxy cluster. Are all of them like little jellyfish galaxies? Some of them seem to be like most of them have some offsets inside of a galaxy cluster. So I found that very interesting. Also, how does this actually affect the cluster itself? So will it affect, say, the heavy element content of the intercluster medium? Because stars form so these big massive blue stars form super heavy elements as they evolve. Does that change what the gas looks like as that gas is ripped off? How does it homogenize? Is the gas sort of going its own way for a while, or does it immediately mix in with the rest of the intercluster gas? Kind of hard to tell at this stage with our technology, but it is a big question. So these are all of our questions. There's more, but I didn't want to have wall of text for you all. So since this can be very difficult to do, we do need help. We professional astronomers, and this is why I'm really happy to bring this to all of you, the astronomy nerds. Please help us. One particular way you can help us in particular with jellyfish galaxies or galaxies with weird morphology is to join up with Galaxy Zoo. And basically what Galaxy Zoo is doing is they show you pictures of galaxies and you pick out what they look like. Like, are they spheroidal? Are they a disk? Do you see anything weird? Does it have a ring? Does it have tidal tails? And that helps us pick out these galaxies. I try to program something to analyze the shape and morphology of galaxies, and it's impossible. It's impossible to do with just the without something like deep learning or AI. And some astronomers are doing that. But in order to build this AI model, we need a really large data set of these galaxies that have been classified by volunteers. And we could make we could make graduate students do it, but there's only so many graduate students and they only have so many years and they need to they need to write a thesis. They can't just classify galaxies for us all the time. So if you have some extra time and want to look at some pretty galaxies, you can help us out. Also, I have a friend at U of T who is building one of those AI models, and he says that they need some more data. All right, so key points, the few things that I want you to come away with, because if you're anything like me, you'll listen to a talk and be like, oh, that was very interesting. I remember none of it. So galaxy clusters are made up of hundreds to thousands of gravitationally bound galaxies, a dark matter halo, and a very, very hot gas envelope around it that appears red. Galaxies and clusters tend to be redder, older, have lower amounts of star formation, and older stellar populations. That means galaxy clusters will affect the members of them. Jellyfish galaxies are sort of this in action. Jellyfish galaxies are the result of a galaxy falling into a galaxy cluster and having all of its gas ripped off of it. So this force is called ram pressure stripping. It pulls on the galaxy and it pulls on the gas of the galaxy and slowly rips it off depending upon how fast the galaxy is moving through it and how dense the gas it is moving through is. And so we're ending with SpongeBob because I had to make more jellyfishing jokes and our favorite galaxy running from him. And so while I said that there wasn't going to be interpretive dance, I am going to do a little bit of a demonstration. So I chose my outfit somewhat carefully. I guess I should Alt Tab here so that y'all can see me. All right. Yeah, let's turn the light on real fast. All right, so I chose my outfit rather carefully. And when I gave this talk at a drag show, I wore something maybe a little bit showier, but I didn't feel like doing that today because it's college campus. Feels a little rude. But so I have my socks, which are black, which it sort of forms the basis of my galaxy. I'm pretending I'm a galaxy. My dress is full of stars, so I look like I am made of stars. And I have my robe of hot gas. It's even red. Hydrogen alpha. So I'm just going to sort of pretend that the air in this room is the intercluster medium. And as I move quickly through the intercluster medium, I have tendrils and it'll eventually come off. But I keep all my stars. All right, so I think that's all I had to say for everybody.
That takes about a billion years, right?
It's actually quite fast. Ram pressure relatively is a bit of a fast process. I would say within the million-year mark at most.
That's good.
I'd like to thank Leo very much for
Thank
that.
Get have our seats. Stop socializing, damn it.
No having fun.
Yeah. Back up business.
All right. Who has questions or comments or wants to chat? I'll start with you.
We're showing examples of a spiral entering a cluster. Do we know of any mergers of ellipticals, they say, going through that same process?
Oh, yeah, absolutely.
I imagine that would be a way to revive it, right?
Probably not. So usually when a revival happens, it's because they've accreted a fresh source of gas. So it's more that they would be hitting some. So they would enter something a bit more like a filament of gas rather than a cluster, unless it's a very young cluster. So young clusters have more cool gas, but the problem is that like mature galaxy clusters have way too much hot gas. The gas is far too hot to actually form stars. So it won't collapse well. I hope that makes a little more sense, but so we do see galaxy revivals where galaxies that were previously dead sort of form like a zombie galaxy. But that's only when they take in fresh gas. But I would say that the gas in a cluster isn't fresh gas. Again, too hot. Won't fall on an actual galaxy disk and form stars.
And if you could repeat the question because it's.
Oh, yes, I can repeat the question.
Okay, so in a galaxy, a spiral galaxy, certainly the stars are orbiting And so they're being held, if you will, by orbital momentum at a certain distance, more or less, right? But in a supercluster, you're implying, it sounds like, that basically everything's falling in towards the center in time. There's very little organized orbital motion that holds them at bay.
Okay, so is there organized orbital motion that's holding this galaxy cluster together? Is it the same with galaxies?
Stopping the galaxies from moving towards the center.
Yeah.
Like if they were orbiting around the whole thing.
I mean, all right, so, what are they like, so why are things falling towards the center? So actually, you're not quite right with the galaxies themselves. It's not orbital momentum that's holding them together. It is actually gravity that's holding them together. It's just that there's so much mass in the dark matter that's how they stay together. If there wasn't dark matter, this is sort of the problem with dark matter and galaxy structure. If there wasn't dark matter, like galaxies and the structure of the universe, it wouldn't really work. So there has to be some sort of missing mass, or we vastly don't understand gravity, which also I wouldn't put past physicists. So you were asking though about the cluster level though. The cluster level, yes, it's mostly random motion. Are you hearing me okay? Okay. It's mostly random motion, like you were talking about. It isn't really an organized orbit so much. Everything is still on that plunging orbit toward the center of the galaxy cluster. Mass wants to move toward the center of mass of a system. That's physics that we learn in graduate school. You always want to move toward the center of mass. So that's really what's going on. It's just everything's moving so fast. They don't all go into the center at once, and they have an initial velocity and position that they're entering from. So they may not be falling directly toward the center. It might be a glancing path, but then the gravity affects it. That will make it fall. That will make it fall into it. So it's all stuff that you have to play around with, like galaxy simulations, to see what this will look like. This is also sort of the problem with like modeling a free body problem or something like that. It can get a little chaotic when you have one body in a system. So what you need is like a supercomputer. This is very difficult to figure out by hand. Yes.
Yeah, by the way, wonderful talk.
Thank you. I'm glad people liked it.
Oh, yeah. Okay, at one point you said that eventually a galaxy will lose all of its gas. Now, considering the lifespan of galaxy, has that actually happened yet? Did any have lost all of their gas? Or is that just theoretical?
Yeah, all right, so I talk about as galaxies eventually lose all their gas. Has that actually happened? So all of the gas might be a little bit of an exaggeration, but there's not enough gas at the rate temperature that it'll form stars, is I guess a better way to say it. Again, yes, we absolutely see that. Those are the red and dead galaxies, those big red ellipticals. Those tend to not be forming stars, and there's so little gas in them that we really can't detect it. Sometimes there's gas that just isn't the right temperature to form stars, though, as well. So maybe I shouldn't have said no gas at all.
Okay, oh, that's good.
Yes.
You showed the image of the tendril going back to 160,000.
Yeah.
What happens to them eventually? Do they form part of another galaxy that are just dispersed?
Okay.
What does one?
Okay, so we looked at the long tendrils that go about 260,000 light years past. What happens to the gas or the galaxy?
The tendrils.
Oh, to the tendril. So what happens to the tendrils after they're pulled off? We don't actually know. So my educated hypothesis, though, and this is something that a lot of astronomers probably would agree with me on, is that in addition to intercluster gas in a galaxy cluster, there's another part of there's so many parts of a galaxy cluster. There's also something called intercluster light. And that intercluster light comes from stars that are not bound to any particular galaxy. So these stars that form from that ram pressure stripping, I think, form that intercluster light as a galaxy cluster forms. Many galaxies are falling in. You get many stars that are formed during that process, and that forms that cloud of intercluster light. So that's what I think is going on. And I also suspect that the gas the gas probably goes on its own way for a little bit until it forms an equilibrium with the temperature of the gas around it, and then it probably merges with the rest of that gas.
Thank you.
Yeah, so that's my educated guess, but we don't actually have, that worked out quite yet, so guess in the best. Okay, so, in galaxy structure, why do we say that the bulge has older stars and the disk has younger stars? So we can tell that by looking at the colors of the stars, and so, well, it's really stellar populations are what we're looking at. So we look at the amount of light that comes from bluer wavelengths versus the light that comes from redder wavelengths. And if something is primarily dominated by super red galaxies, there aren't a lot of young stars forming, so we assume there's not a lot of star formation going on. And young stars don't live as long as old stars. So these super big blue stars, while they have more gas inside of them, they burn hot enough that they actually go through all of that gas way faster. The red stars that can be formed at the same time, they live longer because they just don't go through it as fast. They're one of my mentors in graduate school who studied M-dwarf stars. Those are the smallest of the red dwarf stars. She would tell us no M-dwarf star has died yet. I don't actually know if that's true, but she's the expert. Whereas these blue stars only live for about 50 million years. Oh, only 50 million years. That's nothing in cosmic time. So when you see a lot of blue stars in an area of the galaxy, that means that there's ongoing star formation, most likely. Lots of young stars. There are also red stars in that, but they're outshined by all of those blue stars. And so that's why we say that since the colors are so different in the bulge and in the disk, that the bulge has primarily an older stellar population and there isn't ongoing star formation because we don't see a lot of those blue stars. But in the disk, we see a lot of blue stars, so there's definitely ongoing star formation. Did that answer your question?
Yeah, kind of.
Yeah.
All the younger ones.
Yeah. Why are the younger stars in the disk and not the bulge? That's actually an area of science that we're still studying. But what we think is going on is that these galaxies actually start out quite a bit smaller. And so they sort of grow from the inside out is what we're thinking. So everything inside formed first, and then it's going outward as the galaxy grows with time. So yeah, that's why we have younger stars sort of on the outside of the galaxy rather than on the inside. Inside outwards is what we call it. Okay, all right, wonderful. And in the back, and then I will you, and then you have been raising your hand for a long time. I'll interview you.
I'm confused by the gas itself,
Yes,
so.
so am I.
You don't need to finish my question. In the picture you showed, you've got that long trail of gas, it presumably has been generated over an extensive period of time. When we think of the Balmer series, for instance, we think of light being released because of the combination.
Yeah.
You've got these very rarefied circumstances, you can't pass energy from one molecule to another. How is it something stays luminous for millions of years without obvious ultraviolet radiation to excite those molecular properties? Is there a quantum aspect of the temperature of these gases?
Ooh, that's a very good question. I'm probably gonna need to review some of that. You got it at Balmer stuff, nice. But yeah, so you're right about the Balmer line. So when you're looking at those hydrogen lines, hydrogen alpha and the Balmer line, it only glows for a certain amount of time because sometimes you actually photoionize it, which is what you were talking about. So what's keeping this ionized? What's keeping this glowing? At least some of it is because of the heat, the frictional heat. So that's the one I'm aware of. The other ones I might have to get back to you on. I hope that answered your question a little bit. And there's still ongoing star formation in some parts of it. Because you saw maybe the little clumps of star formation, that's where those blue stars are. But that big long tail, that wasn't actually Balmer lines, that was X-ray lights.
Which is presumably more energetic, therefore hotter.
Yeah,
And
but all the rest of the gases as well.
it seems strange, but it must be radiantly energy cooling over time.
Yes,
But again, it's so different from the gases that we're familiar with.
it is.
Is there a half-life of
Let's see, it's not so much a half-life. How would be the best way to put this? It's more that they emit certain temperatures, certain wavelengths of light based on their temperature. And that's the temperature that they are emitting from.
Is the whole tail more or less the same temperature?
That's a good question. I actually don't know
It
that.
looks the same.
It looks about the same temperature. It must be about the same temperature because it was released at around the same time cosmologically.
Like, really.
Good, cosmologically. Just order of magnitude between friends. A billion years is actually a lot cosmological. The universe is only 13 billion years old. Okay, all right, so we had a few other people racing there. I'll start with you because you've had your hand up forever.
When the two galaxies collide, right? What happens to the supermassive black hole in the center? And what role do they play in the final shape of the galaxy?
Ooh, very good question. So we're actually kind of studying that now with those LIGO detectors, with gravitational wave detectors. And I don't know quite a lot about that, but we do know that, for example, Andromeda actually has two supermassive black holes in its core because of something like that. Andromeda loves eating its neighbors, and so it actually has a double core. So I think that that's eventually going to merge and form a very, very big black hole, and release gravitational waves. But so that's what goes on. But the actual merger itself, the black holes actually are only a very small part of the total mass of the galaxy. So it doesn't really seem to affect the overall merger very much. It's just later in time they will eventually merge if they're close enough. Does that help? Right. The question was, what happens to black holes during the merger? How does it affect the merger itself? Very good question. All right. And
If all the stars in the galaxy are in a stable orbit around the center, why are they directly around a spiral but not a ring?
so if galaxies are traveling around, are sort of orderly traveling around, rotating around the center of a galaxy, why do they form spiral arms rather than a ring? So the ring only happens because of the pressure wave, and that's new stars forming. As for spiral arms, this is also another area of active research. This is sort of one of the dirty secrets of astronomy. We actually don't really understand spiral arms all that well. So one of the things that I learned about how, so there's a few ideas of how spiral arms form. Some people think that they could be the aftermath of something like one of those cartwheel galaxies interaction, because you see these pressure waves forming. However, I remember when I started learning about galaxies, they talked about how these spiral arms, they aren't actually like rigid structures. The same stars don't form the same spiral arm. They travel through the spiral arms in sort of denser areas and less dense areas. I always imagine it as actually a little bit like a traffic jam, how like this is also like if I decided to do something to actually help the world rather than astronomy, maybe I could go into like traffic analysis, because it's a little bit like a spiral arm, at least how I've imagined it, because the individual stars and the individual cars pass through a denser area. So these are actually just like pressure denser areas that are preserved somehow through the orbits of the stars. So when the stars get into that spiral arm, they interact with each other gravitationally. And that sort of preserves that spiral arm a little bit. At least that's what I have gathered from the people who are more experts in this subject than I am. But it's still something that is actually something we don't really understand all that well. All right, and there was another person who reads here. You were in front, and now I'll move back. Yeah, you can. How common are these? Okay, how common are these ram pressure stripping events? So ram pressure stripping, well, ram pressure itself is something we actually observe on Earth. That's how we know a lot about it. So you can actually see it on Earth scale events. But I'm not really an expert on that. It's more physicists who work here who work with that. There's a reason why I'm not good at Earth sciences. But as for the actual rate of galaxy mergers, it's actually less common than you would think, but it's not uncommon. I don't have the actual number off the top of my head. This is also, again, another area of kind of active research, because you would kind of think that a galaxy in a galaxy cluster would be subject to more collision, right? Doesn't that make sense? It turns out it doesn't. Turns out, nature likes to make things as difficult as possible for us astronomers. Instead, what I've learned from more experienced galaxy cluster people, is I was thinking when I entered galaxy clusters, oh, this is where all the mergers are gonna be. And I had professors quickly quash my brains and tell me, no, actually, these galaxies are moving too fast to hit each other. Yeah.
But-
Yeah, it's just you see more mergers because there's more galaxies. But it's not actually a higher fraction of them that are merging. It's just that there's more galaxies in one place, so you're more likely to see it. Yeah, so that being said, it still seems wrong to me, like in my own head, but I'm wrong about a lot of things. Welcome to science. All right, so behind you.
I think you answered my question. I was gonna ask, why is the gas so hot? But then we talked to keep, it made me think of the sun's corona, which is millions of degrees, and people are wondering why it's so hot. So why is that gas so hot in the cluster? But I think you answered a lot of that.
This is actually a little bit of a different question. The gas is super hot inside of a cluster, so I'd say. Again, it's hotter than I think the sun's corona even. It's because all of that gas is trying to get into the center region of the galaxy cluster where all of the gravity is trying to pull it toward. And because it's compressed, it gets hot.
Isn't that very attenuated though?
Attenuated power.
Like the density is very low. It's one molecule per,
Oh, no, the density is very high inside of the galaxy cluster.
no, of the gas. I mean.
Yeah.
Oh, it is?
Yeah. Yeah, no, it's a very extreme environment inside the galaxy cluster. It's nothing at all like if I went into the center of the galaxy cluster, I would be vaporized.
Other than the temperature, like what kind of pressure are we talking?
God, man, you all ask such good questions. I don't actually have a number off the top of my head. I should talk to y'all another time about galaxy clusters and write all of these down so I can actually like have like your questions answered on galaxy cluster section. That would be an interesting thing. I could look up all of these and talk to some other galaxy cluster people and get all of these answers, because it would be nice to have a number or like a simile for how vaporized / crushed would I be if I transferred to a galaxy cluster.
You're dead.
Yeah, I would definitely be dead. I would not exist. All right, and I have one more in the back.
I think some of my question is kind of it's hard to understand that when I think of space, I think of like two molecules that never interacting together because it's so far apart space is big. So how do they actually meet together? But now you're saying that in certain regions of space you're gonna have huge amounts of gas, very dense, so perhaps.
It's that the galaxies themselves aren't very dense, but the gases. I hope that makes it a little clearer.
It's kind of hard to understand how two stars can collide.
Yeah,
But
the gas does.
The gas is flying.
Yeah, it's just because the stars are these little, I say they're all, so like we model stars in point sources. I mean, they aren't actually point sources, they have sides, but like cosmically you can model them as little points. Because they're these tiny little things relatively, because we're tinier little specks. In this vastly far apart, whereas gas can spread itself out more, and that creates that allows it to collide better. So, like for example, when I was doing my little demo, I sort of spread out my outerwear. And that's sort of how gas can be a little bit as well. It spreads out more than stars, which are kind of pointless. Does that answer your question at all?
But then the dark matter doesn't interact with each other. It's the gas that's still to the right.
Kind of. So the dark matter actually acts a little bit like the galaxies. And the problem with dark matter is that we can't figure that out. The only way we figured out the collisionality of dark matter, so this is about the collisionality of dark matter versus gas versus stars. We only know this because of looking at something like the bullet cluster and noticing that where the dark matter should be via weak lensing isn't where the gas is. So we think, oh, it's probably not interacting with anything. But I've taught, oh God, I took a class with an astroparticle physicist, never talked about astroparticles. They talk to, so the astroparticle physicists I've talked to have talked about their models involving self-interacting dark matter. And based on, you can look at much closer galaxies to us to try to figure out how that is shaped inside of the galaxy. And I'm not entirely sure of the details of it, but supposedly based on the shape of the dark matter potential, you can actually figure out whether the dark matter is interacting with itself or not. So hopefully that's interesting. I have a question here, then I will get you.
Okay, then that's it.
Okay, okay.
Okay, you said that if you were in a super cluster, you would be.
I would absolutely be right.
So you mean the central part of the super cluster, because technically we're in it, or we're just revolving around it, Milky Way and Andromeda, et cetera.
Okay,
We're not-
why am I not currently being vaporized? Since we're kind of in the structure of the supercluster, right? Okay, why am I not being vaporized? Because we're just too far away from those hot
Okay,
regions.
it was actually a two-part question.
All right, perfect.
Does the supercluster, everything does it eventually collapse into the center, into one, whatever, really dense, whatever?
No, actually, all right, so does everything eventually collapse into the center? No, because otherwise you'd get a black hole. No, everything's moving too fast, first of all. So,
Oh, okay.
yeah, everything's moving too fast, so it just
Yeah.
flies past and it's moving in space. Because the galaxy clusters themselves are traveling through space, you can really talk about that, but they are. Let's see, when things fall in too fast toward the center of the cluster, that's when you actually get those jets. And that's sort of inflating bubbles with plasma as well. So you actually, there's sort of this galactic fountain effect, that sort of recirculates things. So that also deserves its own talk. All right, and last question.
So,
Okay, so is it necessary for there to be that dense hot gas for jellyfish galaxies to happen at all? Theoretically, no. Theoretically, anything that's dense enough can cause ram pressure, or ram pressure stripping. This is just a consequence of thermodynamics.
So you,
Like you see it on Earth, and nothing gets quite that hot unless you're in a lab.
so you can actually detect jellyfish galaxies outside of that.
I don't think we've seen any jellyfish galaxies outside of that environment, but we have seen very similar processes outside of that environment that cause like that tidal stripping. In particular, in many galaxy mergers, you do see that. So it's sort of like the ones I showed y'all.